we'll come back to the vertex cover problem in this section. And we'll see both a more interesting algorithmic trick in this case, but also one that poses some challenge for the analysis. Recall the very simple FPT algorithm for vertex cover. It was virtually the first example we've seen after the one for SAT. It's the first one where we get something that's not completely obvious. You can branch on the two endpoints. That gives you a search space of 2 to the k for vertex cover. After that, you either have a vertex cover of size at most k, or you know there is none of that size. And vertex cover is a bit, if satisfiability is the standard problem of complexity theory in the classical sense, for fixed parameter tractability, I guess vertex cover is somehow the default problem that people try out tools first. So certainly we can do better than that. There's a bunch of work on vertex cover, but here I'll focus on a relatively simple idea. How to improve the 2 to the k. One option is to have larger base cases. So cases where we can find or argue, reason about the optimal vertex cover sizes without doing a further recursive step. We don't need the exhaustive search. And so consider the case that we have a graph where all the degrees are at most 2. These are very restricted types of graphs. What can they look like? Well, it could be isolated vertices, very boring for vertex cover. It could be a path of vertices. It could also be a path that loops back on itself, otherwise known as a cycle. And it can be a disjoint union of these, but that is it. You cannot build any trees or anything else more complicated, like even a branching of this type, right? That's already degree 3, so that is not allowed. So really it's long chains and cycles, and that's all. Very simple graphs. So what would an optimal vertex cover for this graph look like? Let me add one more vertex to our graph, to our path here. In the path case, you really just want to start not at the endpoints, but if you take every other vertex along the path, that's an optimal vertex cover. You have to pick, for each of these edges that are not the outermost ones, you have to pick one of the 2 endpoints. And the only thing you could potentially do wrong is start with the outermost endpoints. Then you would have size 3 here, whereas 2 is possible. That's for odd length paths. And cycles are virtually the same, except they don't have a start. So you basically start wherever and pick every other vertex. And in the case of odd cycles, you'll have to have 2 adjacent vertices, but that's inevitable. Otherwise, you don't cover all the edges. So what I'm saying here is, if you have these special cases of graphs where all the degrees are at most 2, finding the optimal vertex cover is a linear time algorithm. You just find the connected components of the graph. That's a depth-first search. And then for each component, you learn already what it looks like. Is it a cycle or is it a path? And basically taking every other vertex, avoiding the endpoint is all you need to do. Okay? So very simple and nothing deep there. But somewhat surprisingly, maybe this helps us. The point is that if we solve this special case, we can increase our assumptions for the remainder of the algorithm. What this gives us is that if that's not applicable, then the degrees are, first of all, not in 0, 1, or anything larger than k. This was the reduction we had already in the kernel section. Degree 0 and degree 1 vertices. So these guys are boring, these guys are boring. We can always get rid of them. And high degree vertices, you also knew that, you can always pick that vertex because it wouldn't be feasible to take the neighborhood instead. Plus, we know that there is now at least one high degree vertex, where high means at least 3. That's the new thing. This base case gives us there is a vertex of degree at least 3. Okay? So here's a simple algorithm just based on that idea. It's almost the same algorithm as before, just added a part here. So it's the same kind of depth-bounded search idea. We have a graph and we have a parameter k. How many edges can we still pick? If the graph has become empty, then we can just return the empty set. That's a vertex cover, and it's a minimal one. If k is 0, but we are not in the empty case, then there's nothing we can do. We cannot cover the remaining edges. Otherwise, we have to maybe work some harder. So we check if we're in this easy case. And if so, we know how to solve it. So here I just spelled out in English sentences how to do it. And it's kind of an undergraduate level algorithms exercise to implement that with depth-first search in linear time. So we're not going to worry about the details. The interesting bit starts after that. If this is also not the case, if we don't return here, then there must be some vertex. We might as well pick the one of largest degree. So V is that vertex and W are the neighbors. Now to cover V's edges, we either have to pick V, take V into the vertex cover, or all the neighbors. Otherwise, we don't get these edges covered. And that's what the algorithm uses. There's these two options to recurse on. Either I'm removing V and all its incident edges, or I'm removing all the neighbors with their incident edges, and I guess V alongside with it. And I'm trying to solve recursively the problem where now the graph has some vertices removed, and also the parameter is reduced. By how much? Well, by how many vertices I add to the vertex cover, or the potential vertex cover. So in the case I pick V, I only get a parameter that's one smaller, same as before. But for the second recursive call, where I take the whole neighborhood, I reduce the parameter by at least 3 and maybe more. And that's the magic of the whole base case. It means at least one of the two recursive calls makes more progress by reducing the parameter by more than 1. Okay? Good. Now the question becomes, what's the running time of this method? A few things we can say which are easy. For the worst case, we can assume we're always going to be in the case where we have to recurse further. Say the original graph doesn't have many low-degree vertices. So we're never in this case, or at least we analyze the cost for having that case. We always need both recursive calls. We're not like in the lucky case where one call returns early and already found a solution. And what we'll ignore for the analysis, which is a bit wasteful, but we'll make the analysis easier, is that the graph is shrinking a bit. We're removing some vertices. But remember, so the setup is that the graph is really big and the parameter is relatively small. So the fact that the graph gets slightly smaller doesn't help us all that much. It means that some of the base cases get slightly cheaper over time, but it's not a big difference. So that's just to make the analysis a bit easier, and we're upper bounding the cost of the algorithm. So then what we get is a recursion in the parameter k. The graph we treat as staying the same size, or we upper bound the cost by the original size. But the parameter is what changes, and that's the interesting bit where we make progress. So if the parameter is 0, we pay constant time for the base case. That's just returning immediately. And for the general case, we assume we have to do some linear time, for example, for shrinking the graph or finding this largest degree vertex. So this will be linear in the original input size. And we have the 2 recursive calls, where we reduce the parameter by 1 and by 3, respectively. Okay, so that's set up clear. So if we can solve this recurrence, we can get the analog of what we've analyzed before, where we said the search space size is 2 to the k. Previously, we had for the simple FPT vertex cover, this would have looked similar. We have a base case, and then we have 2 recursive calls of the same size before. And I guess the pre-processing is a bit easier, so maybe we don't need this extra term. But to be generous, might as well include it. Okay, let's call this n and this m in the usual notation for graph algorithms. Okay, now this recursion here was trivial to solve. Okay, one more step we can do to get rid of this extra term is we're basically building a tree. So this is the recursion tree after 2 recursive calls. And I guess the right ones is going on for longer because the parameter doesn't shrink so much, so the tree is a bit lopsided. Now, here, this is a different recurrence, which is easier, which is counting the base cases. So just the number of vertices that don't recurse further. Now, because this is a binary tree, the number of of internal nodes, so the number of recursive calls that do further, so I guess these are non-leaf recursive calls or non-base cases. These are all these other vertices. Their number is bounded by the number of leaves. Because it's a binary tree. So we would normally pay this term, and this doesn't depend on k because of our assumption here. So I would pay this order m cost in each of those red vertices. That's the true cost I have. Okay, and here and here. And I can upper bound it by instead paying it at the green leaves. So tk is effectively this theta n plus m times the number of non-base cases. But that's essentially the same as taking the green ones. It is one less. So we're taking the green recurrence instead of the red recurrence. If we at the end multiply by, so I guess I should have added this part, that's the bk then, right? So if we solve bk, we can just multiply by n times m, or n plus m, sorry. And then we get the overall cost for the original algorithm, or an upper bound for the original algorithm. That's the idea here. And the reason is just that we get rid of this extra term with a different parameter. That makes life a bit harder, and the base cases are easier to count. Yeah, I'm adding here the base case for parameter size 2. I guess if you're asking, here's a graph, can you find a vertex cover with 2 vertices? You might try all pairs of vertices, and that's still roughly within that time bound. I guess it's n squared, but maybe you can do slightly smarter by just going over the edges. I guess 2 vertices, there's like if a graph can be vertex covered by 2 vertices, it's going to be a very boring graph. It can have a single edge. So that base case, I'm technically cheating a little bit. That base case is not part of the pseudocode here. But we could add base cases for k equals 1 and k equals 2, and they wouldn't do anything interesting. On the other hand, what we really do here is find a vertex and do one step of recursion, and we're done anyways. So take this, yeah, question? So yeah, the question was, can you cache the results of the recursive calls as in dynamic programming? And the answer here is no, at least in general, because the input for the recursive calls is different each time. It depends on the path of, you start at some point with the same graph as the input, but then you take away a certain subset of vertices, and there's many different subsets of vertices you could remove. There's too many subsets. So you could formulate it as a dynamic programming instance, but the number of subproblems would be exponential, number of subsets, and so it's not going to help. It's essentially doing the same as this. I wouldn't really reuse anything. Yeah, it's a good point. There's superficially, these algorithms always look similar, but then is a big difference if you have a polynomial number of subproblems or an exponential number. The code doesn't make this so explicit, but subsets explodes. I don't know, what's a number of pairs of integers doesn't explode. That's maybe a typical dynamic programming subproblem, a range of some array. Yeah, so take the recursion with a slight bit of slack. It's not going to give the exact time in the sense we want to analyze algorithms in undergrad introduction courses. This is going to give you the right exponential growth. And it gives you roughly the right polynomial factors. Maybe there's for this case, a slightly higher cost than for the other base cases. But this is not going to affect the overall growth. It's even vanishing in the big O. It's just a constant factor difference. But still, like this kind of recurrence, how do we solve that? This looks much more innocent. It has similarity with the Fibonacci recursion, except that here it's a -3, not a -2. But how should we know how quickly this grows? And this is a prototypical case. Many fixed parameter tractable algorithms of this sort of a depth-bounded search, they end up having the same kind of analysis where there's different recursive calls and you reduce the parameter by different amounts in each of the cases. So you often end up with questions like this. What's the exponential growth of this? Is this better than 2 to the k? So let's find out. And what I want to show is on this simple example, and I'm trying to do it live so that you see the method without any kind of shortcuts. So let's copy the recursion first. We have B2 is B1 is B0 is 1. And we have BK is k minus 3 plus BK minus 1. And we'd like to solve this, or at least get a feeling for the exponential growth. It turns out we can exactly solve this always, whenever the recurrence looks like this. And I want to teach you the method more so than the concrete example, but I decided to do it on the example instead of trying to give the general construction, because I think it illustrates the key points, and then it's not a discrete math class, so maybe some of the generalizations that you would need for the general case we don't care about. Okay. The first step is to do something weird. We're going to define some function which is a series, an infinite sum of this form. And you'll have to bear with me a bit for why. For now, I'm just claiming this is going to help. And this is called the ordinary generating function of that series, of that sequence of numbers. Okay. First objection is this is an infinite sum. It might not converge. It might not be any reasonable value. The short answer is it doesn't matter for the technique. It kind of works either way. The second answer is it will converge if z is small enough. The absolute value of z is, say, 0.01. Then this exponential growth here means we're shrinking these coefficients by so much that the sum still converges. It's a bit like the geometric series converges. If you take a good starting case, what's that series? Does anyone want to shout out? And you can keep thinking while I'm trying to find it on the cheat sheet. I think the series are further back. Might misremember though. Okay, all the lovely integrals. I think it's on the, no, this is basic, is on the front. Oh, but there is some mention of generating functions. So while we're there, I might as well show this part. One more. So ordinary power series is what it's called here. And so you see it's a thing. And there it is. So the same formula also appears under different names on the first page, but this is the one it's looking here. It has an x instead of a z, but that's the only difference. And it can be written in closed form as, okay, maybe let's also take the screenshot just as a proof. Right, so that's just here in tiny because I'm not going to use it that much for now. So 1 over 1 minus z. That's a kind of an algebraic identity, but you can also make out that this, as a function of z, this is going to run into problems if z is equal to 1, right? That's one obvious thing. Then you're dividing by 0. It seems to work fine if z is bigger than 1, even though this thing on the left doesn't seem to make sense. And so the cheat sheet doesn't give more detail on this. Some of these identities here should only be used if z is small enough. But it turns out as an algebraic identity, it works either way. Now this is also the generating function, or the ordinary generating function of a special sequence, namely the all-one sequence, right? Because if you set bk to 1, you get exactly this, and then you can write it in closed form. Which is my proof by example that these infinite sums, they can sometimes converge, and they often have even a nice closed form. So now that's maybe a first hint that potentially you can go from sequences to generating functions, do some math on the generating functions, for example, use formulas for series like this, and then we would need a way back, okay? And we can define a notation for that. So I'm sticking with k. We define this thing to mean bk if capital B of z is the ordinary generating function of the sequence bk. That's just a definition. In general, that's not all that useful. It's a good notation, but it's only useful if we can also get back from the closed form or from some representation of this generating function to the coefficients, the sequence that we started with. And let me switch back again to the cheat sheet because it's right here. In general, there's a way to get back, and that's called Taylor's series expansion. Often people learn about this in engineering math to approximate functions. But here we're going to use it in a different way. So oftentimes, Taylor series are used in the sense of giving some function which may be complicated. Can you approximate it locally by a polynomial? And that's if you stop after some point. It's in general an infinite sum, but you can stop at any point, and then you get a polynomial that optimally approximates that function close to a certain point. So I guess here the point of development is at a equals 0. So is at x equals a, sorry. And that's what this function gives. It tells you in closed form what the best polynomial looks like. Namely, it's written in this form that you have x minus a to a power. So you would have to expand that for the normal form of a polynomial. And then the factor in front is a certain derivative of the function divided by I factorial. So in general, we can get the coefficient back by just using this function here. We use a equals 0 in our case. So then all these just cancel, and it just becomes x squared, x to the I. All right, so if we take b to the z and develop it around 0, I'm just writing this down once so that it becomes a bit more obvious for you. It's b of 0 plus z times b prime, the first derivative, then z squared, then the second derivative of b, sorry, add 0. Here I'm inserting the development point. That should be 0 all the way. Divided 2. Let's do one more. The third is the third derivative at 0. And you divide by 3 factorial, or 6. So in general, if you want the function to be exactly represented, then you should continue ad infinitum with this. But you can also stop at any point, and then you get this polynomial approximation. So this is how normally people learn about Taylor series expansions, especially in some engineering math class. If you've ever wondered how pocket calculators compute the sine function or cosine and all these things, they can't actually compute sine. They compute an approximation using Taylor series expansions. And then they can evaluate the resulting polynomial efficiently. So it's very widely spread, and you use it all the time. But here we're going to use it in a totally different way. We're just using it symbolically. I can get back this kth coefficient if I just have the function by taking the coefficients. So here you see this is exactly the way we would represent the ordinary generating function. It's an infinite sum, and it has the power of z to the k. And then it has a coefficient in front. Let me write the coefficient first. And the coefficient is exactly this kth derivative divided by k factorial. So if we want to plug the coefficient at z to the k, we just have to pick this part, right? So, so far so good. Now, this is actually utterly useless. And the reason why it's useless is computing the kth derivative in the general sense, like, well, I'm giving k as a variable, and I'd like a closed form for what the kth derivative of a function is. And the function is something awkward. In general, this is hard. It's not clear what the kth derivative of something is, and write that down easily. Now, in simple cases like for this function, you could actually work it out, what the kth derivative has to look like, because there's a pattern of the derivatives you can guess. In general, this is useless. But you can use it to compute the first few terms. We're going to use it, so here I'm just making the point, it is possible to get back from the generating function to the sequence coefficients. And there's a concrete formula how to do it. It's just not very convenient to use that most of the time. Instead, what we'll do is start with the sequence, go to generating functions, move around the closed form terms, and rearrange them, and then use equalities like this backwards. And that's going to be all that we need for solving these. And you can use this all as a kind of just a purely algebraic method that doesn't need to involve any derivatives or anything about functions in terms of set. It can be just a way to make use of existing formulas. Okay, this is getting a bit abstract, so let's continue with a concrete example. So what we'll do is we'll start with our actual sequence and try to get something better than this general representation for the generating function. And I'm starting here so that we still have the recurrence here with us. So the general sum is k from, let me just write k greater or equal 0, then bk times z to the k. All we know about the sequence is the first few values and a recursive representation. So we have to use that. There's pretty much nothing else we can do. So I can insert the base cases. Right? This is going to be 1 times z to the 0 for b0, plus 1 times z to the power 1 for b1, plus 1 times z to the c squared, z squared for b2, and then plus the remaining terms, which maybe as a, why does this keep happening? I'll first start just saying symbolically, this is bk times z to the k, but now only summing from 3 onwards. It's worth stressing here. Now, this recursion, I guess I didn't copy it here. This is valid from k greater or equals 3. Because it doesn't make sense to talk about k bk minus 3 if that's not at least 0. But here I have k greater or equal 3. So I can now insert my recursive definition. Okay? So this thing can expand to bk minus 3 plus bk minus 1. And that's what we're going to do next. So I'm continuing this equation for b of z. And we have these terms. So it's 1 plus z squared plus, now these can immediately split. So they're inserted here, but then I can take the sum apart. So there's one sum, k greater or equal 3, bk minus 3 z to the k. And the second sum, k greater or equal 3, bk minus 1 z to the k. And now we're going to try to simplify this to get something back in terms of k. Because this almost looks like the original b of z, except that it doesn't perfectly match. There's a mismatch between the index here and the power, and there's a mismatch in where the sums start. But it's actually close. So first of all, I can pull out 3 sets in front of the sum. And then what I'm left with at least matches in the exponent and index shift. And I can do the same here with pulling out 1 set. So that's good. We're closer to this. The only thing that's now not quite right is this k minus 3 business. But if you stare at this first sum a bit, we're starting at 3, but then we're always subtracting 3. I might as well start at 0. It's the same thing. I'm just doing a change of variables. Replace k by k minus 3. So if I start at 0 instead of at 3, then I'm starting at 0 in each of these cases, bk and z to the k. And here I can do the same, but it doesn't quite work. I still have the sum starting at 2. Now I'm moving in slow motion here, but I think it's worth doing for illustrating what happens. This thing now is exactly the same as b of z. And this thing is almost the right thing. It's just starting a bit late. But we can pretend it's b of z and subtract the first two terms again. So if you want, I can add 0 by saying I'm adding b2 z squared. Sorry, that one's there. b1 z to the 1, b0 z to the 0, and then subtracting the same thing again. All right, I'm adding 0. But then I can pull this together. These two together are now again a b of z. So what I get is b of z on the left side from up here equals these guys minus these, and this is actually 1, right? This is 1. So some things cancel. And then I lost, okay, they don't cancel because I lost track of the factor z here. So that has to go in front of the entire thing. I guess I messed up the spacing now. So this factor I lost, and it should be here. So there's a factor z around all of this, which means these won't cancel. But it's still true that this, together with these, is my b of z. Okay, but first this term, so z cubed b of z plus z times b of z. And then what's left of these? There's the minus z squared and minus z. So I guess some things do cancel out, but it's different things that I previously had. Okay. So we have 1. That's a plus. Where did the minus come from? Oops. Okay. Now that's a lovely equation that I can solve for b of z. And we can try to bring all the b of z terms to one side. So it's b of z times 1, then minus z cubed and minus z. And what's left on the other side is a 1. Well, I know what b of z then is, right? It's 1 over 1 minus z cubed minus z. Oh, so look, the generating function has a nice closed form. And this is something we didn't have before. Now the question is how to make progress from there. And this is something, again, that is somewhere on here. We'd like eventually to use one of those inequalities, and there's a bunch more, backwards. So we're trying to find any of these terms in what we've derived for the generating function and use it backwards to get back to the sequence. Now that in general can be tricky, but the kind of functions that we have make it possible in the general case. All we need is partial fractions. Now there's a formula somewhere on this partial fractions here. So this describes the general recipe. On our example, you can probably do it more easily, or we're going to cheat. So you're going to remember 1 divided 1 minus z cubed minus z. And we take a little help from our friend called computer algebra. And I know there's a function called apart that does this, but maybe we can also do, okay, let's first type was 1 over 1 minus z cubed minus z. Okay, yeah, that's right. Okay, let's see if it can say partial fractions immediately. Partial fractions of that. So people know Wolfram Alpha. It's a lovely tool where you can take natural language input and it translates it into Wolfram language or their mathematical language. So you should always double check if the input that they understood from your query is what you had in mind. But apart from that, the rest is provably correct algorithms. And so here they give some representation. I guess we want to see the approximate form. That doesn't look too useful. But it's what we need. It's just not super nice. It doesn't do it. Too bad. So we'll have to do it manually. And this might not be super nice. Okay. That's the danger with picking the real examples. The thing about partial fractions is we can, if we have a rational function, so polynomial on top, polynomial on the bottom, numerator and denominator, we can always find a representation for this where we have the roots of the polynomial and I guess this is something where I'm going to ask for computer algebra help again. Let's say the roots are z0, z1, z2. Then I can find a representation where it's z minus z0, z minus z1, and another constant divided by z minus z2. And so we need the roots of this polynomial to do that. And I get the feeling that this is not going to be a nice number, because this is a polynomial of power 3, degree 3. Come on. Somehow stuck. So we take our polynomial and we can ask for the roots. That's something it can easily do. Yeah, so it has an exact representation, but they're not very nice. So we'll just take the approximate form. And that's going to make the remainder a bit ugly. So these are the actual values for Z1, Z0, Z1, Z2. Here's the copied bit. So at this point, I'm assuming here this representation to be general. This is if all the roots are unique. Or are distinct. So there's no multiple roots. In principle, you could have a polynomial with a factor set. So what this means is just the roots. You can rewrite the polynomial. This is the same as the product of these three terms. Maybe I should have said this at the get-go. You can just always write a polynomial as factors of this form, but maybe in general you need powers of these. It could be power of 2 here for some polynomials. The nicer form of the partial fractions you get if the roots are distinct. Now in this case, what's ugly about the roots is two things. First of all, there's no nice short representation. There's some algebraic numbers. You can write them using roots, square roots and so on, but they're not nice rational numbers. So there's only an approximate solution given here. Plus, in general, they're complex numbers because you might have square root of negative numbers in there. But they're distinct. You see there's a real root, 0.68, and there's two complex roots with their complex conjugates. One is positive imaginary part, the other is negative imaginary part. But they're distinct. There are three distinct numbers. Also, they're shown here. This is actually useful for another bit that we'll come to later. Here the three numbers are shown on the complex plane. And you see that this one is the one of largest modulus, I guess. Of smallest modulus. This is closer to 0 than these two. That's hardly visible. Okay. Now, in nice examples, you can now solve for A, B, and C and just insert these. In general, you get this if you rewrite the left-hand side using this product. You can solve for A, B, and C just by multiplying through some of these factors and setting set to specific values, and then you can compute the explicit numbers for A, B, and C. Now, in this case, this will involve all these complex algebraic numbers, so it's not going to look nice, and we might not do it because we don't have to. The point is that this always has a nice form. So if we take the first one, this is almost one of the formulas that we had on the cheat sheet. Maybe that's the easiest to see. It's the generalization of the one we used before of this shape, 1 over 1 minus some constant times z. And what we have is close enough to that we have a hope to get it into that shape by massaging terms a bit. So we try to get it in that shape. Well, we can divide by z in the full set out here. What do? We divide by z0. And multiply by -1. And now we have it in this form. The constant is 1 over z0. And we have some factor in front. But that's actually just a factor you can pull out. So if you look at the representation for our generating function all the way at the very beginning, if you multiply each of the sequence entries by 2, you can pull out the 2 of the sum and you get 2 in front of the generating function. So multiplying the generating function by a constant multiplies each of the sequence entries by the same constant. So multiplying by a constant, as we do it with this minus a over z0, that's going through all the way to coefficients. So we can, formally we can say we take the coefficient of this a, this term a divided z minus z0. That's the same as taking coefficients on this thing, because they're the same functions. But also it means I can pull out this factor a over z0 and then take coefficients of what's left, namely this part with a 1. Okay? And now I'm using that this has the form, if I said z to 1 over z0, I get that it has this closed form. So taking the coefficient just gives me a c to the power I. So the coefficient here is this thing, as before, and then that becomes just 1 over z0 to the power k, the power we extract. Okay? We'd have to do this for the other summands, but that's another cool property of generating functions. If you have a sequence where bk is the sum of two sequences, ak plus ck, then also the generating functions add up, because you can split the sum for the two parts. So second property that we're using here, plugging coefficients in b of z, the actual thing we want is plugging the coefficients in this plus the coefficient of this plus the coefficient of this. Okay, so let me sketch this. Our bk, the answer we want is the coefficient of b of z by definition. And that's going to split into terms of this form for a, b, and c. So it's essentially this term 1 over z0 to the k. Then we have the same for b and for c, where I'm just replacing what the constants are. Running out of space. And out of time. 1 over c2. Okay. Now, what does that help us? First of all, it's a closed form representation. It has some annoying constants that you really only want to deal with computer algebra. But they're in principle computable. These are just constants that come out of the partial fraction representation for this rational function, and the roots of a polynomial. These are easy to, if you just want to get numbers, you can easily approximate them. But the second thing is, these are simple functions. They're all exponential functions. Right? This is some number to the k, some number to the k, some number to the k, and then a linear combination. For large k, what will happen for large k? Only the one with the largest base of the exponential growth will be relevant. The others are exponentially smaller in the literal sense of the term. So this will be asymptotically the same, or let's get rid of the constants in the same way. And let's say it's just 1 over z0 is the one that has the largest absolute value. Let me write it like this. Come on. A lot of calculations. Assuming that the absolute value of this root is larger than the absolute values of the others. I guess smaller. We want the reciprocals to be larger. The one that has the largest reciprocal is the one that dominates the growth, and that's the one that has the smallest absolute value. Right, okay. So you take these three roots, and you find that this one is going to have the smallest absolute value, you would have to compute the square these two, add them up, and take the square root, whatever that works out to. But this one's going to be the dominating factor. We could try to do that, but maybe in the interest of time, let's not do it. So 1 over this number is the exponential growth of our bk. Okay? And I guess there's no way to do this without keyboard. Okay, let me at least get the number. So 1 over this one, 0.68233. Yeah, okay. If you want to copy out, then you have to pay their subscription. So it's 1.465. That's what I wanted to note down. So what's the point of all of this? The exponential growth of the cost of our running time here, of bk, is going to be this 1.46 whatever to the power k. And that's substantially better than 2 to the k. Right? You can plug in some numbers. Maybe this algorithm is still doable for k equals, I don't know, 50. Whereas 2 to the k, maybe 20 at best. So we bought a bit of larger sizes we can deal with. Good. To wrap this up, you can do the whole analysis we've done in general if you have any recurrence of this form in the general case. And I'm just writing this down so you don't have to always go through generating functions. If you design algorithms where you have this structure, you recurse on different parts, and the sizes of the parameters drop by different amounts, di, you can immediately just invoke this result. In general, you can explicitly give the Tn in terms of some constants and powers. But basically, it's the same problem. You get a polynomial, and you have to take the roots of that polynomial. What we'll usually use is just this corollary. There's the power, the exponential growth is the root. Here's a different polynomial. So here is actually largest absolute value of the root. And the factor, the polynomial factor, is the multiplicity of the root. So you can shortcut all the generating function fun to just this final result here. And if we do that in our case, instead of 3 slides of calculations, you just take this polynomial from the theorem and plug in the numbers. So the characteristic vector here is 1 and 3 because we make the parameter smaller by 1 and 3 respectively. So we get this, and we solve for the roots here. And you get the same ugly numbers, of course. Okay? So that's what we've proven. For the total time, same is true. And yeah, the polynomial time is not so important. But now we've reduced the exponential growth substantially. And you know how to analyze these sequences.